During the last few lectures, we've been talking about this idea of the mole. Using it in practice, a mole of something is equivalent to its mass in grams. So if we wanted to have a mole of water, we know that we could go into the lab and weigh out 18 grams of water from its molecular weight, allowing us very easily to convert from macroscopic quantities, the gram, into microscopic quantities, the molecule, where mole is used as a surrogate for molecules. Now, this isn't saying mole is the same as a molecule. The mole is a counting number. So instead of having a dozen molecules, we can relate a dozen molecules to a dozen molecules. This allows us to relate a mole of molecules to another mole of molecules. So it's the meat of our conversion. When we convert from one chemical quantity to another, we go through this mole-to-mole conversion. And that's going to be central, and we'll return to that in a few minutes. But actually, what is the mole? The mole turns out to be the number of particles found in exactly 12 grams of carbon, 12. So we fix that number as the number of particles in exactly 12 grams of carbon 12. And what this does is stack the deck such that, so something that weighs 12 AMUs is 12 times as large as something that weighs 1 AMU. Similarly, with the mole, something that has 12 moles has 12 times as many particles as something that has 1 mole. So we can use this as a sort of scaling factor. It turns out that that number of particles is 6.022 and change times 10 to the 23rd particles. And we give this the name Avogadro's number, or Avogadro's constant. And this number can be determined experimentally from a number of different cases. Turns out it's very useful in relating atomic level events to macroscopic events. So we now have two competing definitions for what the mole is. So the mole of something can be related to grams of that compound via the molecular weight of that compound. But the mole is also related to a number of particles. Using Avogadro's number, we can relate that to numbers of atoms. So what this allows us to do is to relate now all the way back down to the molecular level. We can go from grams into moles using the molecular weight, and then drag that all the way down to numbers of of atoms. Now we can start counting atoms if we so desire. And this is exactly how we use Avogadro's number. The reason I didn't talk about it, even though it's central to chemistry, Avogadro's number is often overkill. We usually don't utilize it, except in the case where we're talking about counting atoms. So right now, what we see is we use the mole to convert between chemical entities, whenever we convert from one substance to another. But we've learned that we can use the molecular weight to convert grams of some compound into moles. But we can also use numbers of atoms. If we could count atoms, we could use that as well. And this is where Avogadro's number comes in. And we can turn the crank the other way and spit out numbers of atoms and masses in the same fashion using the molecular weight and Avogadro's number. But central to this is this mole-to-mole conversion that stems from our chemical equation. So now we have an alternate way of finding the number of moles, and that's using Avogadro's number. So let's try one. All right, the average number of molecules in 1 milliliter gas sample is 2.46 times 10 to the 16th. So if you take a little, about a, yay much of gas, literally about yay much, and the sample was pure oxygen. So we're just going to assume that it's pure oxygen. Again, oxygen is one of the diatomic molecules. Molecular weight is 32. If the sample was complete, what would be the mass of the sample? Now, with these problems, we're not asking density. The volume doesn't play a real role in this, the 1 milliliter sample. What we really care about is the 2.4 times 10 to the 16th molecules. Now right here is a huge hint that this is an Avogadro's number related problem, because the only way to convert from molecules into moles is Avogadro's number. So if you see the word molecules or atoms, then you can probably whip out Avogadro's number, but not before. So we can use Avogadro's number, 6.022 times 10 to the 23rd molecules. 6.022 times 10 to the 23rd is probably effective for most things we're going to be doing. You don't need to. You should memorize this one. Of O2 is defined as 1 mole of O2. And then using the fact that 1 mole of O2 is equivalent to 32 grams of O2. Again, this is our molecular weight statement. This is Avogadro's number relationship. We can spit out the mass of that compound. 1.31 times 10 to the negative 6th grams. Or, for those of you who are conversion junkies, 1.31 micrograms. So not a lot of mass. That little bit of air doesn't weigh all that much. That's Avogadro's number in a nutshell. Very limited use. Look for the word molecules in a problem.